Okay, so this is question number 1. Okay, so we're first going to tackle the part about the radius of convergence. So to calculate the radius of convergence and the interval of convergence, we're going to use the ratio test. So this is setting up the ratio test. The limit is n goes to infinity of that times that should be less than 1 in order for the part series to converge. And so we're just going to solve the limit. Now the x plus 2 to the power of n is cancelled out, and I just grouped the n terms together, and that's going to go to 1 because the limit as n goes to infinity of n over n plus 1 is just 1. And if we just simplify the expression, it's just going to be that. And if we solve for x, we get that interval. But we also need to test the endpoints of the interval to see whether they converge or diverge. So we're going to do that next. Waiting. Okay. So let's first test the radius of convergence for x equals -3. This is just simplifying the equation. This is, as you can see, because of that, it's an alternating series, and we're going to use the alternating series test. And we know that 1 over n squared is a decreasing sequence. So if we perform the alternating series test, the limit of that goes to 0, and so we know that the above series converges. So -3 is in the interval of convergence. Now we're going to do the same thing for x equals -1. And if we simplify the series, it's going to just be 1 over n squared. That's just a p series of p equals 2, which is greater than 1, so it is going to converge as well. Yes. Yeah, I know, it's going to converge to pi squared over 6, just as a side note. So both -3 and -1 are in the interval, and given that a is an integer, we now have 3 integers to test for a, which are -3, -2, and -1. I'm just waiting for myself to write down what I just said here. Yeah, the possible values of a are as follows. And so we're going to test each one of them for their conditional convergence. Yeah, okay. So we're first going to do a equals -3, and the series is going to be as follows. As you can see, let's first test for absolute convergence. So we're going to take the absolute value, which is going to get rid of the -1 to the power of n term, and it's going to be n equals 2 to infinity of that series. And let us use the integral test to test the convergence or divergence of that series, the absolute value. So we're going to take an improper integral of n equals limit of as n goes to infinity of 2 to n for that integral. And we're going to use a u substitution with u is ln x and du is 1 over x dx. And if we apply u substitution and try to solve the integral, which I'm doing in my head for some reason. Okay, I'm doing it as a side work because I'm not smart enough to do it in my head. Okay, so we're going to get that as a result of the u substitution, and if we plug in the n and 2, we're going to get that value, which is obviously a converging value. So we know that since the integral converges, the series converges, so that when a equals -3, absolute convergence exists instead of conditional convergence, so that rules out a equals -3. We're going to do the same thing for a equals -2, and we're going to test the absolute convergence for this series as well. So getting rid of the alternating term, we're going to set up the integral test for that because it's also going to decrease the 1 over n times ln squared of n. So the integral test works, and we're going to apply u sub as well with the same u value and same du value. Same work. I'm just waiting for myself to finish up. Yeah. Oh, and there's I made a mistake in the writing the improper integral, but I'm going to fix it later anyway. Yeah. No, e to the n equals to n goes to infinity. Yeah, okay. So if we plug back in the values, we know that this value converges as well, so the integral converges and the series converges as well, which means that there's going to be absolute convergence as well. So that leaves a equals -1. We know this is the answer, but we're going to check it anyways to see if I'm wrong when I made the problem or not. So because we're going to assume that this converges conditionally, we're going to set up both the absolute and just the normal convergence test. So we're going to test the alternating series test for just the normal series, and we know that as a limit, because we did the alternating series test, it's going to converge. And we're going to do the integral test for the absolute value of the series that we're going to use, and we're going to do the same thing, same u sub process. Yes. Yeah, I'm just waiting. So we're going to get the ln of n x, as from n to 2, but since limit as n goes to infinity, so the integral diverges, and so we know that the series conditional converges as a is indeed equal to -1. But we can also use an integral test by setting up, instead of 3 separate integral tests, we're going to just simplify it into a generalized form of x times ln of a, and we're going to do a u sub, and we're just going to set up the, instead of 3, 2, 1, we're going to generalize as a, and the form comes out very similar. It's going to be as follows, and let us just plug back in 1, 2, and 3 for a. If we plug in 2 and 3, it's going to produce a normal value, as you can see. Yeah, that's just the work. Yeah, the numerator is going to hold the actual value because of the highlighted part, it's going to move downwards, and so yeah, it's going to converge. But when a equals 1, everything just doesn't work, as you can see. Okay, so that was problem 1, and we're going to now move on to problem 2. If you have time, please like and subscribe. Yeah, I just wanted to say that.